In the experiment titled Synthesis of Stereoisomeric Transition Metal Complexes, we're going to apply inorganic synthesis to the problem of creating transition metal complexes, and specifically we're going to use two reactions to synthesize two sets of stereoisomers, a pair of diastereomers involving a cobalt complex and a pair of enantiomers involving an iron complex. And in addition to learning the techniques of inorganic synthesis and trying to achieve a high yield as usual, we're also going to explore differences in the properties of isomeric compounds. These ideas are generalizable, so when you get to organic chemistry, for example, you can apply the relative properties of, for example, a pair of enantiomers or a pair of diastereomers to organic compounds with these relationships as well. And while we won't do any formal characterization of the properties, you'll be able to look at things like the color and the solubility and, for example, the polarity to get an idea of the similarities and differences between enantiomers and diastereomers. We've seen that stereoisomers have the same connectivity and the same connections between atoms, the same bonds, but different positions of the atoms in space, different three-dimensional structure. And we can distinguish two types of stereoisomers depending on the nature of the relationship between the two structures involved. If the two structures are mirror images, then we're looking at a pair of enantiomers. In fact, you carry around with you a pair of enantiomers every day in your hands. So I'm not doing a great job of drawing this, but if you look, for example, at your own hands, you should notice that first of all, they're mirror images. If you reflect one through a mirror, you get an image that looks like your other hand. If you've ever looked at your right hand in a mirror, you'll notice it looks like a left hand, and vice versa. However, and most important for this discussion, those two mirror images are non-identical. In other words, you cannot superimpose your hands perfectly. That's our criterion for being identical. You can't overlay them perfectly such that everything matches up. If you try to match up, for example, your middle fingers, all of your other fingers get thrown off. If you try to match up your thumbs, all of your other fingers get thrown off. So these are non-identical mirror images, or enantiomers. If the two structures under consideration are not mirror images, which of course catches everything else that's not a pair of enantiomers, then we're looking at diastereomers. To show you an example of diastereomers from sort of everyday life, I want to consider an example involving Legos. So if you've ever looked at Legos before, you know that they have this kind of blockish structure with these little circular or cylindrical projections coming out of the top. And we're going to look at two Legos connected to one another in two different ways. So first I'll draw a black Lego here, and next I'll draw a red Lego connected to it in two different ways. In the first structure, we're going to put the two at a right angle, like so. And in the second structure, we're going to put the two in parallel, like so. If we look at how the Legos are connected in both structures, we see that they both have the same connections. They both have four linkages, you might say, between the black and the red Lego. However, the arrangements of the Legos in space are different, as evidenced by a difference in this angle right here. There's a 90-degree angle here, there's a 180-degree angle in the structure on the right. So, although these have the same connections, they have different structures in three-dimensional space, and so these would be a real-life example of diastereomers. So not only are these non-identical, but these cannot be interconverted by reflection the way enantiomers can. If we imagine putting a mirror between these two structures, for example, if we reflect the left-hand structure through a mirror, we're going to end up with something that still has this 90-degree angle. And likewise, with this structure, we're still going to end up with a 180-degree angle, and so these cannot be interconverted by reflection. In this experiment, we're going to synthesize a pair of enantiomers in one reaction and a pair of diastereomers in another reaction. And what I want you to think about at the end of the synthesis is not just what's my yield, but think about the relative properties of the two enantiomers. And separately, in the reaction that synthesizes diastereomers, what are the relative properties of the pair of diastereomers? What do I mean by relative properties? Well, I want you to think about and observe in the products whether some of the following properties are the same or not the same. The color of the two complexes, the phases of the two complexes, and by extension the phase transition temperatures, the melting point and the boiling point. The solubility in various solvents. We're going to take advantage of differences in solubility in one of the syntheses for separation purposes. Related to that, the polarity. So look at the molecular structures. Consider the differences in the molecular structures and think about whether you would expect the polarities of the molecules to be the same or different. Finally, consider the separability. And this is related to the polarity and the solubility. Do we have the ability to separate the pair of molecules based on things we've learned so far? In the first part of this experiment, we're going to synthesize a pair of diastereomeric cobalt complexes. They both have this formula given here, but they're going to have different three-dimensional structures, and they'll be diastereomers. The chemical equation for the synthesis is given here, and it looks pretty complicated, so I want to talk briefly about what's going on here. We're going to start with cobalt chloride in aqueous solution, and I've just represented that here in a beaker. We'll talk about the operational synthesis here in a second. We're going to combine that with ethylene diamine, which we're going to abbreviate EN, hydrogen peroxide, and hydrochloric acid. Now, one thing we should notice is that in cobalt-2 chloride, the cobalt has an oxidation state of +2. Cl is -1, there are two of them, so cobalt has an oxidation state of +2. But in the product, there are two chlorides within the complex, but the chloride that's acting as a counter anion tells us that the total charge on the cobalt center here is +3. The oxidation state is +3. So an oxidation has occurred. And that's the point of both the H2O2 and the H+ within HCl. These combine to serve as an oxidant, and we end up with H2O, which you can think of as a reduced version, quote unquote, of H2O2. The other purpose of the HCl, and the purpose of the Cl- counter ion here, is just to serve as a source of Cl-. We need chloride to serve as a counter ion within this complex, and we need two of them, in fact, to balance everything out. So how are we actually going to accomplish this synthesis? Well, it's not quite as simple as dump everything in and stir it and go from there. There's actually a specific order we need to follow in addition of the reactants. The first thing we're going to do is add the ethylene diamine. What this does is start a process where the ethylene diamine, which is a Lewis base, coordinates to the cobalt center, and we start getting cobalt-ethylene diamine complexes. At some point we want to stop that process so that we don't get too many ethylene diamines on the cobalt center. Ideally we want to end up with two, right? And at that point we can stop further coordination by oxidizing the cobalt-2 to cobalt-3, and that's where we add the H2O2 and begin the oxidation process. Shortly after that, we're going to move to the hood and add HCl. It's very important to do this in the hood because we're going to be working with fairly concentrated HCl, 6 molar, and we're about to generate HCl, hydrogen chloride gaseous fumes, in the next step. So at this point, we'll have a relatively large volume of reaction solution in here containing ethylene diamine, H2O2, and HCl. Over time the product forms, however, in aqueous solution we can't simply precipitate it out. It's soluble in water and it likes to remain in water. The way to get around this is to concentrate the solution, that is, remove the solvent. This accelerates the reaction by making everything more concentrated and drives off the solvent, forcing precipitation of our desired product. So we're going to heat the reaction solution to a boil. This absolutely must be done in the hood because as we're driving off water, vapor, we're also increasing the temperature of the system and decreasing the solubility of gaseous HCl. That's going to drive off HCl gas, and we definitely want to whisk that away in the hood. Once we've concentrated the solution down almost to dryness, but not quite, you'll notice some solid coming out, and you'll notice very thin wisps and eventually somewhat larger crystals of a green solid forming in the bottom of the beaker here, along with a little bit of water. You want to leave a little bit of water in this. And once we reach that point, we're going to wash the crystals with cold methanol. Methanol is CH3OH. The purpose of this is to separate the two isomers. At this point, we actually have a mixture of the two isomers here, and we want to separate those two isomers so that we get pure trans isomer as a solid product. After that wash with cold methanol, we're going to vacuum filter, and this is really where we physically separate the products. So what we end up with at the end of this process is in the filter flask we'll have the methanol, which was used to wash, as well as the cis isomer. The cis isomer is soluble in methanol, and so this will be in solution, but you'll notice a color change that indicates the cis isomer there. And As a solid left at the top of the filter, we'll have the trans isomer. Be sure to make observations of the filtrate and the solid trans isomer before discarding these, and be sure to find the mass of the trans isomer to measure a yield. Very briefly here, let's talk about why these complexes are diastereomers. So in the product you'll notice 2 ethylene diamine ligands and 2 chloride ligands. Ethylene diamine is a bidentate ligand, and so it binds at 2 points. Because of its size, it can only bind at 2 adjacent points. In other words, it has to bind at 2 points that are 90 degrees from each other, something like this. So there are actually multiple ways for the ethylene diamine ligands to bind to the complex. We could, for example, have both ethylene diamine ligands across from each other like this, leaving the chlorides in sort of the axial positions. You can think of them like that. This is one possible isomer. We could also have the chlorides bind in more of a cis orientation, close together, with the ethylene diamine ligands bound in kind of a cis position as well, like so, and this is the cis isomer. So these are the 2 isomers we'll synthesize in the course of this reaction. In the second part of the experiment, we're going to synthesize an iron oxalate complex in which the complex itself is actually negatively charged with potassium counterions in the solid as well. The procedure here is much simpler than the cobalt synthesis. We're simply going to mix the 2 reactants in this case, aqueous iron trichloride and aqueous potassium oxalate. There will be water around as well, and those will combine in what is basically a ligand substitution process in which the chlorides are replaced by oxalate ligands. C2O4 2- is the oxalate ligand. Here it starts out as basically C2O4 2- as a free aqueous ion, and in the product it's coordinated to iron. The chlorides start out coordinated to iron but end up in aqueous solution in the product. So this is basically a ligand substitution process. The synthesis itself is very simple. We simply mix the products and then cool them down using an ice bath, and this promotes crystallization of the product as it's not very soluble in water, especially at low temperatures. Once we've got that solid crystallized out, we're going to vacuum filter to separate the filtrate, here in blue, which has nothing of interest to us really, just KCl, and the solid product, which is this potassium iron oxalate complex. Now, the iron oxalate complex is chiral, and in the course of this synthesis, we're going to synthesize both enantiomers. To demonstrate that it's chiral, we can again start from the octahedral lattice that we should expect for this product. So oxalate, C2O4 2- is a bidentate ligand. It can bind at 2 points. Like ethylene diamine, it has to bind at 2 adjacent points, 2 points that are 90 degrees from one another. When we have 3 oxalate ligands bound to a central atom, we have an interesting case where 2 enantiomers could form. So there are 2 distinct ways for the oxalate ligand to bind to the iron center. And as we'll see in a second, they're enantiomeric. So let's try to be as systematic as possible here. If we lay down the first oxalate ligand, which I'm just going to abbreviate with a line connecting the 2 positions it's bonded to, if we draw that first oxalate ligand in the same position, trying to make these as similar to one another as possible, there are 2 ways we could lay down the remaining 2 oxalate ligands. We could take the bottom position and connect it to this position pointing towards us like this, or we could take the bottom position and connect it to the position in the rear like so. If we then connect the other 2 positions, we end up with 2 complexes that are not the same. You can imagine these like fan blades designed to move in one direction versus fan blades designed to rotate in the opposite direction. These are not superimposable and they're non-identical, but they are mirror images, and I'll let you verify that on your own. Try building an octahedral model using a model kit and use some simple connections like string or rubber bands to connect the octahedral positions together and see if you can generate and verify these enantiomers. We won't get into the nomenclature here, but the 2 enantiomers are distinguished in a nomenclature sense using the delta and lambda symbols. The solid we isolate from the synthesis will be a mixture of the delta and lambda isomers, and see if you can distinguish visually these isomers within that solid.